Hi there, so today we'll be talking about the sine rule and we will be giving some background information on where it came from and what it is used for. So the sine rule actually has numerous names. So most people do know it as the sine rule or the sine law, but there are also sine rule formula, the sine formula, and the law of sines. The law of sines is a very common name for the sine rule, and so if you were to do a little background information on your own, possibly through a search engine, then you might want to take into consideration these different names as well instead of just the sine rule. The sine rule can be used on all types of triangles, so it can be used on acute triangles, obtuse triangles, and right triangles. So it can be used on all types of triangles. Doesn't matter what type. There is certain information that needs to be needed in order for you to be able to use the sine rule. So either two sides and one angle must be known, like this picture here. So I have the side of 8, the side of 7, and then I have one angle here of 47 degrees. And so this information can be plugged into the sine rule formula, and then our x value for this angle can be solved. Or you need to know two angles, like here in this example, we know two angles, 47 degrees and 43 degrees. And then we also need to know one side, so the 8 here. And so you can use this information to find this x value here that corresponds to this angle here. So that information must be known in order for the sine rule to be useful. What many people don't know is that the sine rule, so A over sine A, B over sine B, C over sine C, is actually equal to this value D. And so D is the diameter of the circumcircle. So what the circumcircle is, it's the circle constructed where it incorporates all three vertices of the triangle. So I have my vertice A, B, and C here. And so those all lie on the circumcircle. And then the diameter, this green line here from T to S, is actually equal to our C over sine C, B over sine B, and A over sine A. So those are what those ratios are actually equal to. So many times the reciprocal is actually used to solve problems. So a lot of the time it's written A over sine A and so on. But the reciprocal can also be used because sine A over A, sine B over B, sine C over C are all equal to one another as well. And so it's really convenient to write it this way if, let's say, you were solving for an angle rather than a side, because then you already have your unknown value on the top and ready to be isolated. I just wanted to cover the proof of the sine rule for acute triangles because many people don't actually know where the sine rule came from. They see that it's a rule and they just start to use it. So I wanted to actually cover the proof of the sine rule. So we're going to base it on this diagram here. So this is just going to be for acute triangles. And then we just have H1 labeled here, which creates two right angle triangles. So we can agree from the SOHCAHTOA rules that sine A equals H1 over C, right? Opposite over hypotenuse is our C value there. So with a little rearrangement, H1 equals C sine A, right? So similarly, you can do that for this triangle here. So sine C equals H1 opposite over hypotenuse for this triangle is our A value. And then we rearrange, H1 equals A sine C. So therefore, since our H1 equals C sine A and our H1 equals A sine C, we can make those equal each other. So C sine A equals A sine C here. So we can do a little rearranging, divide both sides by sine A, divide both sides by sine C, and we get A over sine A equals C over sine C. So similar reasoning shows that A over sine A equals B over sine B, and therefore the sine rule for acute triangles is proven. So proof of the sine rule for obtuse triangles is a little bit different than for acute triangles. So we have this diagram here, and so what we have to do is we actually are going to extend the side AC over to the right a bit so that it connects with vertex B. Okay, and so now if you look, it creates a right triangle as a whole. We have these two angles here, which are actually gamma and delta, and they're supplementary. So it holds true that sine gamma equals sine delta. And also, sine gamma is equal to h1 over a, which equals sine delta. So we have this to hold true because of our SOHCAHTOA rules as well, right? We have our delta here, which is equal to opposite h1 over hypotenuse, which is a, and that in turn is equal to the sine of gamma because we know that sine of gamma and sine of delta are equal to each other. So with a little rearranging, we have h1 equals a sine gamma. And we just want to note that sine A equals h1 over c, so h1 equals c times sine A. So the sine A equals h1 over c also came from our SOHCAHTOA rules. We have our angle A here, opposite h1 over c, which is right here, our hypotenuse. Thus, we have A sine gamma equals C sine C, because they were both equal to h1. And therefore, with a little rearranging, we have A over sine A equals C over sine gamma. So therefore, similarly, we have A over sine A equals B over sine B equals C over sine C, which is our sine rule. So this whole thing is the proof for the sine rule for obtuse triangles. And we just have our references here. Thank you for listening. I hope that it was informative.